day to you. This is Galactic bringing you a special presentation on this Friday, August 23rd from Chico, California. Today we'll be getting a definition of time, which will supersede that of Albert Einstein, who was the first man in history to ever give a characteristic to time that could be proved mathematically. Now, in our attempt to get a definition of time, you'll see over here that I have two overlaid screens. The top screen is just an advertisement of what is coming up in September, where Galactic will attempt to supersede our current knowledge of the anomalous magnetic dipole moment. This is actually a dimensionless quantity that's been measured to 0.001, and there are no units. It's dimensionless, which means it's a pure number. So this is of ultimate fascination to all physicists. Probably Richard Feynman made the most famous statement about this, although he was not specifically talking about this rather strangely named number. It's a measurement that can be taken. It's an excruciatingly small measurement. It is among the smallest measurements ever made. And I'm just going to scroll up here so you can see that there is an equation on which it's based. And then two things you'll see here. This formula, that's an identity. And this diagram, which I won't click on because it will expand, but that's a Feynman diagram. So that is essentially a number which we will be exploring in upcoming presentations here at Galactic. Today, we are not going to be dealing with the anomalous magnetic dipole moment, but we will touch upon it in a sense as we cruise through our eightfold path to getting a definition of time. It is necessary to have a path to get a definition of time. One of the most elusive quantities, phenomena, whatever it may be called, it's somewhat paradoxical even to name what time is, because it does not fall into any class, not even an abstract class, unless, as can be done, I won't attempt to do it, but one can manufacture a pseudo-class if one thinks one can get away with it. But that's more or less the philosophical aspect of time. It's quite difficult to analyze. So I'm going to take a big swig of water, and then we're going to get, for the first time in the history of physics or mathematics or science, a cogent, rational definition of time. This is obviously a theoretic attempt, because if I'm successful, I'll be the first man ever to have done this. So to begin, I'm going to close off our advertisement, and that's really all it is. The anomalous magnetic moment is closely related to this number, the fine structure constant, about which Feynman spoke, but they're so closely related, it will help us to know the difference between the two because of a specific numeric relationship between these two quantities. The fine structure constant has a value of approximately 007. And it's not necessary to be more specific than that. We can use the James Bond code for this number. It's 007. That's the fine structure constant. That's not specific because it is an irrational number, as it would have to be, because it is based in curved geometry. So that's our introduction to what we're going to do today. I'm simply going to end our advertisement for the upcoming Galactic and Extragalactic Interactive Online University, AEIOU. AE for short. Galactic is how I usually refer to it. It's my little institute, which has been operating for a little over 2 years on YouTube. This will be a presentation of the definition of time. But we are going on. There's a lot to cover in the future. And I just want to assure you, you will want to tune in because Anagalactic is entering a synthetic phase that's synthesizing what physics actually already has, and that's the goal. Because you have to build on what you already know. I'm not off in some ivory tower somewhere. So this is a major turning point in the history of this peculiar geometry I discovered, which is simply spherical geometry. That will be the basis of our approach today, right now, just in one video, a definition of time. So to close off our advertisement, we will be studying the fine structure constant. I have a very specific approach to getting a meaning for this number, and a meaning is being sought for this number right now. The fine structure constant is related to the anomalous magnetic moment by a specific irrational constant number. That has been pointed out, it's obviously well known, but it's quite odd that it's not emphatic, it's not emphasized, that these two numbers are actually the same number. And I will be proving that probably in September. We're going to get the definition of full meaning of the fine structure constant that makes geometric sense. So you'll want to stay tuned for that if you're interested in true cutting-edge science. All right. So what is the constant number that relates the anomalous magnetic moment to the fine structure constant? One is 007. The other one is 001. That's the beginning of the Secret Service symbolic code name for the hired killers for the British Empire. Magnificent hero to have, right? There you go. So 001 and 007 are related on the number tau. The number tau is a known number. It's been known since the time of Euler, which Americans, I understand, particularly on the East Coast, pronounce Euler. Well, that means you're a provincial, backwards, bad representative of the United States of America. You pronounce that name correctly, you stupid, overeducated Harvard, Yale brats, Princeton included. It's Euler, you monkeys. Thank you. And it's Schrödinger, Erwin Schrödinger, dum-dums. And it's Gödel. Sorry. All right. So to close off our advertisement, what is tau? It's 2 pi. So the exact relationship between two of the most mysterious and important numbers ever discovered in the history of science are related on a constant that I fully understand. And that will be part of our sequence. You're going to understand it too. So I hope you're excited. You should be. So I will make sure I follow through on my implicit promise there. You will be excited. You're tuned in to the right channel. This is Anagalactic, bringing you the secrets of the universe and now the secret of time. So I'm just going to turn this off. We're now done with our advertisement for the anomalous magnetic dipole moment and the fine structure constant. So gut. And this is our outline, the eightfold path. This is stolen right out from under the nose of the standard model particle physicists who have a eightfold path that if you fall into it, you'll never get out. It's a labyrinth designed to kill you. So you don't want to go the way of the standard model anybody's. That's just a little warning to you who are still rational. Eightfold path is also stolen right out from underneath the noses of the Buddhists and the Taoists. The eightfold path is an ancient term which I now own. It's my term now. So the eightfold path will now describe the transition from Bronze Age science to Super Space Age science, and I will be the master of that transition as it's beginning to occur right now, right here. So we're going to go through this quickly so that you don't get baffled. The most significant aspect of this sequence which we're now going to follow quite closely is all embodied in this column of numbers. And I'm going to highlight that in red, bold. So we have 8 items: time, universe, quantum, atom, and then the second section, geometry, continuity, perpendicularity, also called orthogonality, and then the Boschkovich force curve. So let's begin. This will be to answer the question, what is time? Mathematically, the mathematical definition of time. In order to understand the mathematical definition of time, you have to understand what mathematics is capable of doing. And that will be part of this sequence. I'm now going to turn this off. These are the 8 I'm going to follow myself as I give to you now in as brief but optimally long. It's quite a balance, quite an art to get a definition in a short amount of time. I could tell some anecdotes about how some men have run up to 5 or 6 hours and worn out their audiences. Yeah, Feynman was one of them. So we don't want to wear you out. We being I do not want to wear you out. That's contrary to the purpose of science. So without any more further introduction, we now begin a formal definition of time. Time is perceived by an ordinary human from childhood to old age. We all perceive time the same way existentially. It's an arrow. It only goes forward. It's continuous. Now, we need to catch up with what science knows about time, which is quite easy to do because there's only one transition point. Albert Einstein, of course. Albert Einstein introduced the world to his mathematical construction that unified space with time, which means that time must have some kind of characteristic, which is a fancy way of saying something like a property. Is it indeed a vector? Can it be represented as an arrow, as we, from children onward, perceive time? All humans apparently perceive time in the same way, as a forward-moving arrow. It's not spatial, it's temporal, so it's a different domain than what we see. But we can see time indirectly. How? By motion. That's actually profound, but this is a good introduction. Time is related to space. How? Linearly, believe it or not, which should be a bit surprising because the line, you know from youth, is somewhat an artificial object. We perceive a straight line according to how we've trained ourselves in geometric perception, which is Euclidean, which means linear, which means distance. So that's all quite simple and obvious. But in science, a large percentage of it in communication is stating the obvious. So there is a phase where you're forced to state the obvious, to show where you're beginning logically. And we're trying to get a logical approach to time. Well, Albert opened the gate because he's the first man who ever attached a characteristic to time. What is it? It's related to space. Well, you might ask, quite reasonably, how is it related to space? The answer is geometric, of course, or you cannot visualize it. Now, I can also tell you, as is well known, of course, all of this is well known, but we want to be sure we're all on the same page, so we continue on the same trajectory. It's quite important in communication. All right. So time is related to space on a right angle. Albert said and proved Using calculus. That's very important to use calculus. Well, we all know that, but it's very important to know that and bear it in mind. That Albert began with the 3D conception of space. That's Euclidean. 1 line, 2 lines, 3 lines. He added a fourth, which is imaginary time. It turns out that works. So, to say that that's profound is somewhat cliche and artificial, but I would like to pause here to grok on that for just a moment. That what we perceive as space, which just goes out and out and out, or if you're looking in, like with a microscope, in and in and in, well, both of those have limits. You can only look out so far. That's the visible edge of the universe, which the James Webb Telescope is currently probing. And doing a good job returning some very good data. It's ultimately fascinating. I strongly recommend keeping up with the photographic records that man is getting of further and further out towards the edge of the universe, which haven't found it yet. So we have that limit. Infinite spatial outwardness. But when you look in, there's also a limit. And that's has several names, but we think of it as the quantum limit. It's an inner limit of perceptibility and measurability. Where does time fit into there? It doesn't, but we're going to find out where it actually lives. Now, what Albert discovered is that if you linearize space first, which is what we do, he inherited the 3D system. Albert was versant in strict, well-known linear geometry, so he fully accepted the grid system. It's a grid. It makes cubic space. Yes, that has a mathematical meaning, of course. Well, you may have heard the cougar. She's up on her perch. She may be leaping down here. We want to get it. See if we can get this. There's the. Oh yeah, here she comes. Whoa, man, was that worth seeing? All right, there's some free entertainment. You don't pay anything here. All right, that's her lab cat and her tail. I love this cat. She brings life to the lab, you know what I mean? Everyone should have a lab cat if you have a lab. She's still got her tail there. Come on, honey, that's the keyboard. Yeah, there's her tail. All right, so there's some free entertainment. This is the Anagalactic Circus here. We have a wild cougar here, alive and running free. Inside, bending her tail towards the camera. Okay, she's down on the floor now. I may have to let her out. Cats like to go out from time to time. All right. None of this is going to be edited. All of this is history being made right now. We're going to get a definition of time. I'm not kidding. All right, so we have space-time. What is that? Well, it's 4D. Now, on our second item, don't worry, we're coming back. Obviously, we're coming back to that. Space-time, well, that's currently where time lives. But it lives on a line in artificially composed cubic space. But it sure works well enough with calculus. Actually, hypercalculus, but whatever. On item number 2, we have the universe. Now everybody wants to know about the universe. It turns out you're not going to get out of that. You have to first know what the universe is. Well, nobody does. So we're going to have to do that first. It's easier than you might think. The physicists haven't figured it out, but I have. So that's item number 2. You see that the universe points to infinity? It certainly does. All right, so the quantum, that's number 3, is to breeze through this, and then this is necessary. Trust me. You got to trust your professor. Well, it's dangerous. What if I'm a kook nut? Oh, then you're inside shape. Trust me. So the quantum, another rather mysterious word. Quantum, what is that, an adjective or a noun? Yes. Is it an adjective or a noun? Yes. So I have it pointing towards superposition. That's obviously a decision that I made because quantum points at a lot of things. So that's what we'll be dealing with. You're going to understand infinity, which nobody does, the quantum, which nobody does, the universe, which nobody does. Space and time are incorrectly perceived, you're going to perceive them correctly. And item number 4, the atom, which obviously points at something going in. It's the proton. The proton is the key to everything. And so I'm going to teach you what the true proton-electron relationship is. So that's 5 things that nobody knows that you're going to find out right now. And we're also going to touch on the photon just slightly. Imagine why. Because light fills the universe. All right. And light speed is very important. Well, we're going to understand it all because that's where time is. In part 2 of our 8-fold path, the last 4 items, what I call the second semester, is geometry. Geometry, you need to know first what that is, because that induces the orientation to the framework which we're going to compose ab ovo sui generis. We're going to manufacture an integral form of science, integral geometry, integral mathematics, and integral perception, so you can directly perceive reality using a couple of tricks. Okay, so there is a trick involved. You have to trick your mind to see reality. I can tell you this can be done. You're going to do it. But it is voluntary. You don't have to. You can refuse to see. So it's up to me to present this so that you'll understand it. The definition of time is geometric. Now, Albert got a geometry. It's linear geometry. Is there any other way to perceive the universe other than the way Albert Einstein did? Well, to answer that question, you have to know how Albert Einstein perceived the universe. Not as a human, but as a member of the scientific community using the consensually agreed upon system. That is called Euclidean 3D spatial geometry. It's called Euclidean because Euclid was the first man to axiomatize the system. It stood the test of time, I'm pretty sure you're aware. Long enough to get to Albert, who accepted it without question, that the 3D geometry is the best way to formulate the universe in terms of geometry, which is the mathematical system. So these seem to be an identity. They are. The line and our whole system of mathematics are identical. Now, in order to accredit that, you may or may not accept that at face value. So let me give you a clue so that you can consider it more closely as being actually an accurate statement. It is an identity of a kind, but it is 2 different data types. One is a spatial object. That's called the line. Very obvious. What about our number system? How does that relate to the line? It is the line. That is our number system. But what makes it so interesting is since the line is an object, you can have more than one to fill space. And if you use 3 lines that have a specific relationship called orthogonality, then you can compose a cubic system of numbers. That is what science uses. A cubic number system for volume space, which is the universe. Now, what Albert added to the mix, he took the 3D cubic geometry that all science uses from before Albert and ever since. He added a 4th orthogonal line, and that has to be imaginary because the 3 lines fill the space we do see. We don't see the 4th linear axis. We can't see it with our visual perceptual system. It's not your eyes. It's your visual perceptual system, which blind people have too. They're missing the use of the eyes, but they still have their visual perceptual system. And can use it just as well as a person who has vision. Okay? So vision and visual perception are not at all the same thing. Everybody has visual perception. Not everybody has full use of their two eyes. That is not an ultimate limitation. All right. So now we've gotten to the number 5, geometry, and you now have a fairly good idea, I would presume, you may already have had it, that numbers only exist in a geometry. The geometry comes first. Hierarchically, the way we process information, the end point is never numbers. The only time a number has direct significance is when it's a distance, and then the straight line makes sense. It's a line segment. From your telescope to the star is a specific straight line distance. Now, that's where all of our numbers live. They live on a straight line, but is that where numbers all are? Are they all that way? No, because of something called superposition. You can actually have two overlaying systems. We do. I proved that in 2022. It's remarkable that I am the one to have proved that, because it's rather been staring us in the face the whole time. I think you can probably see why. A straight line only makes sense if it's embedded in a higher order space. Well, that's spherical, obviously. It is, actually, truly. That's part of the secret of time. We're getting there, and we're about halfway there now. Geometrically halfway there. So our number system is a one-component system. It has to be, because that is what a distance is. It's a one-component linear number. 4 units on a line makes a distance. That's really all there is to it. That's Euclid. That's about it. You can dig into it and get much more. It'll be more complex the more you study it. The number system is quite profound. But that's where they originate. They're all on a line, including 0, which is a problem. We're getting there. So to go on to item number 6, we have the line. Really, I call it now linearity, because it's more of a human concept, which does make sense, obviously, but it is a human concept. Well, it's a human concept that's actually embedded in another concept, a higher order space, which is not linear. It's spherical. Okay? And the line is embedded in the sphere. It's called either the diameter or the radius, which is a 2-to-1 relationship. Very profound, but we're getting there. Item number 7 is the universe's interpretation of what linearity implies. If you want the geometry of space, you're going to be talking about not just this, where it's plus and minus. You see, that's in item number 7, the plus-minus relationship. That's called polarity. You can see it's 180 degrees. This is plus, and this is minus. They're balanced. Now, perpendicularity is when you have one line that's perpendicular to the other line. That's called orthogonality, and the symbol for it you see is a little pipe with a lower bar. That means perpendicular. That's how I use that symbol. And to close off our eightfold path, so we now have a full blueprint of basically one single sentence I'm going to say afterward to get a definition of time going through this sequence, is the Boschkovich force curve. The Boschkovich force curve will be talked about for a long time to come, because Boschkovich really did something even better than Einstein. And you'll see that I have 2 indented bulleted items with a strange symbol, a circle with an X through it. That means sphere or spherical. Spherical is the counterpart to linear. because a straight line is straight, but a spherical line makes a surface. So a circle is a reduced form of the sphere. And it's remarkable to be able to say this, but it is true, that the circle is a linearization of the sphere. You have a sphere, and think of it as being between my two hands. Well, if I collapse that sphere, it's now a straight line, but if it's actually not, you can't see the other dimension. That it is saying a lot. I want to do that again because this is your visual introduction to where time is. It's actually between my two hands. This is a sphere. If you linearize it this way, you end up with a straight line, correct? But you know that it's actually a circle, because if you're doing this and you linearize the sphere, it actually doesn't change shape the way we see it. It's as if you took the moon and you collapsed it to a circle. Would you be able to tell? You would if you looked at the surface of it. It would contract in a way. It would actually form a specific shape. Because the surface of the moon as we see it on a full moon is half the moon. But it looks like a circle. Well, imagine if you collapsed that so it still looked like a circle. The interior would change, but the profile would not. It remains what you saw before. It's still a circle. So that's the relationship between a circle and a sphere. I don't want you to be distracted by this. Time, universe, quantum, atom. Break. Geometry, linearity, orthogonality, force curve. All right. We're now ready. So to get a definition of time, we'll now be in good shape if we can catch up with what physics already knows. Albert did that for us. This is actually not complex or complicated, but it most often is presented in such a way as to baffle the person who's hearing it. So I'm going to attempt to explain what is space-time so that it makes perfect sense. I don't know why it shouldn't. Well, that also involves the notion of general relativity, which is a bit more abstract, but it certainly should be no challenge. And it also relates to gravity. All of these being bound up in the EFE, the Einstein field equation, which we call spacetime. So, what is spacetime? It begins with cubic space and adds a fourth imaginary orthogonal line, which represents time. So we learned two things from that. Time has been linearized by Albert, and he already by default linearized space. So the relationship between space and time is a linear relationship between two linear quantities. The linear quantity of space is distance. The linear quantity of time is time. It's not the second. The second does not exist. It's an artificial term that never should have been adopted at our level. So when explaining this, you never refer to a second. It's totally arbitrary to talk about a second. So the unit of space is what again? Is it distance? The same objection could be made. Is space quantized? If you're using a linear number system, you have to quantize space. That is called distance. Distance. It's also called length. Length and distance are synonymous. But you have to understand something at the outset. It's well known. It's just not often stated. The way that we perceive space in science is as a quantized quantity, which is redundant. But is space indeed quantized? It has to be to measure it. That's what a measurement is. It's some form of linear separation. Now, when I say some form of linear separation, you can extend the concept or perception of linear spatial separation to include another data type. That's what Albert did. He linearized another domain that's not spatial. He linearized the contra-domain. How did he do that? If you can answer that question, you will get a definition of time. Currently, there is no definition of time, except you can say something about it ever since Albert Einstein showed us how. You can say that linear time is perpendicular to linear space. So time and space are related geometrically. Is that just an illusion? Because that's a hard right angle. I hope you realize what perpendicularity implies. It means that time is going on a straight line, even as we perceive it as humans. It does fly as an arrow. Although it's hard to say more, it just seems to always go forward. Well, that's shown in the space-time diagram. But then what's perpendicular to it would be, in a 2D projection, a straight line. Two lines. Perpendicular. But I think you see the problem. The perpendicularity of the domain of time is perpendicular to a cubic space. That makes the domain of time perpendicular to completely filled cubic space. Well, that means there's an imaginary dimension. What does that mean? Well, we can't directly perceive it. Here's why. We only see in 3D. We only see on the horizontal line. We don't see that the horizontal line is moving. That's called the frame of reference. You have to have a center in order to measure anything, either space or time. You have to have a frame of reference. In the cubic system, we know exactly what and where that is. It's 0. So that's the center of the linear system. It's the center of all 3 lines for space. It's the center of all 4 lines for space-time. That is not curved. So how did Albert get at the curvature, which is an aspect of this relationship? Let me ask you something. Is space curved? Could you say for sure if space is curved or not? What about time? Is time curved? Well, in the space-time formulation, neither one of them is curved. Time is a straight line, and all 4 lines are at right angles to each other. That means that time is orthogonal to each one of the 3 spatial lines. Obviously, it's imaginary, but you can see that there's a sort of a spherical relationship there that was intuited by Albert. But the way that you get at the curvature, because a gravitational field implies a curvature because it has a spherical center. Gravity radiates out, you could say it this way. The force field is exerted from a geometric center in spherical space. So he's composing a formula for that, implying the curvature of something. So which one is curved? Are all 3 spatial dimensions curved? Is time curved? What is curved? Well, what Albert did was he applied the calculus to the grid in order to compute the 4D curvature. Well, you might guess that that's probably a really difficult equation to compute. It is extremely difficult. But it can be done by supercomputers. That's actually what's done in computing. Where is general relativity used? Do you have any idea of what use it is? It's used in space travel. So, and GPS, which is a form of space travel. Those satellites are traveling through space around the Earth. Well, then you're going to need general and special relativistic corrections. Those are routinely employed in all of your GPS actions. You're using special and general relativity. You're using Einstein's field equation, which has time and space at right angles. Does that seem artificial? It is, and that's why we use the calculus. That's why Albert invented a new form of calculus, hypercalculus, to get 4D curvature. That nobody had ever even thought of that. Well, Minkowski did. So Albert wasn't the first, but he and Minkowski had an interesting relationship. You might be interested in that. But that's what we have. That's what we inherited. Nothing has changed. Nothing has changed at all since 1915 in our knowledge of time. There's been no progress at all, because what can you say besides what Albert said? That's what we're going to do right now.
Is complete the work of Albert Einstein.
I could tell a story. I'm not, though. I don't want any anecdotes. I'm tempted, oh boy.
So we begin with Albert's formulation of time. It's perpendicular to space. What does that mean? Okay. In order to understand the role of time in space-time, you first have to understand the role of space. Albert did something to space when he added time to the formula. It puts a characteristic to space that it is now in relation to something else, time. Now, both of those are linearized quantity. They have to be. You have to have linear numbers to compute anything. That's what linear numbers do for us. They give us the ability to compute. So space is not linear, but science thinks it is. So we begin there. Is it linear or not? It's superposition. It's both. You can do either, but you shouldn't do both at once. Well, Albert tried to do both at once because he had no choice. What we would like is to avoid all those complications. You can do that by integrating the notion of linear volume space, which is cubic space, okay? It is. It's cubic. Obviously, that's not a match on sphericity. No. So we do have to reapproach the Euclidean basis. Well, that would be non-Euclidean geometry. So we talked about that in the previous lecture, so I'm not going to go into the 3 definitions of non-Euclidean geometry. That's quite an overused and undisambiguated term. When talking about dimensionality, we're talking about linear dimensions. This is 1D, this is 2D, and this is 3D, and then 4D. I always do this because it's imaginary, but it's a form of complexity using an imaginary component. You have to if you're computing time into volume space. One of the numbers has to be imaginary. The way it can be done is either time, space, or space-time, because you have 4 numbers that represent space-time. It's a 4-number system. It's a 4-component number. Actually represents a position. But that's ambiguous. It's actually a position in space-time, not space. It's a position in space mixed with time. And that forms a specific geometry called pseudo-hyperbolic geometry, extremely difficult to visualize. But it does have a reference frame. So Albert did not complete his work. He never got a universal reference frame. What he got was a general reference frame for any frame of gravity. And that works for local space if you use calculus to shave off the edges to get the curvature. So that's rather simple, I think, to understand. This is not this. And there's a specific relationship between the two. Now, we're getting there. So we've made some progress here to bring ourselves up to speed with what science knows about time. It's artificially linearized because it had to be composable into a linear systematic space, which is now called 4D spacetime. It's a linear system. Technically, the geometric term is hypercubic numbers. Hypercubic numbers. This four-component number system is hypercubic. And to complete my previous statement, this is time. If you take time out, you have ordinary 3D Euclidean just grid space. If you add this, you have a super grid. But this has to be negative. So these three are positive because they're distances. Distances are always positive. So these three parts of the four-component number are positive numbers. But this one, time, is negative. So the orthogonality is complexified. And that's deep, but you will accept what I say because I've fully researched it and you can check. So I'm not trying to hornswoggle you here. That actually is the right way to say it. Time is not linear. It's been linearized. And space is not linear. It has been linearized. And that's the story of science. It works on Earth so well, we're convinced it will work in universal space. But universal space has two characteristics that are strongly related that makes it utterly different from our computable space. And that is the inner limit and the outer limit. And that is a spherical concept, as I will now show to you, so that you will remember it literally forever. This is the correct, non-Euclidean geometricization of universal space. Non-Euclidean. So we're going completely outside the box. What I can tell you to begin with, and this is necessary, we do not lose linear space. I proved that in 2022. I consider it to be one of the most important discoveries in the history of geometry. And here's why. You're now going to know what I know. In order to compose space, we immediately encounter spatial infinity, which stops us in our tracks because it's imaginary. That is, we cannot conceptualize it, therefore we cannot measure it. There's a bit of philosophy involved there, but I think you understand that infinity can't be penetrated with the human mind. But it is there. We call that imaginary, and that's our first axiomatic statement. That the infinite extent of space, the characteristic that it goes on seemingly forever, as we will say, and that's significant too, that we say forever, which is a temporal term, not spatial. Forever isn't spatial, but that's the way we say it when we talk to each other. That space goes on forever. That's actually correct. And here's why. Infinity, as you look towards the edge of the universe, as our James Webb telescope is continuing to look farther, but it's always there's going to be farther. Is there an edge? There has to be an edge. I proved that. So accept that as the second axiomatic statement. The edge of the universe is infinite. The edge of the universe is imaginary. Those are the only two things we can say about the universe at its outer extent. It's infinite and it's imaginary. And now we're going to make a number that simply is that and see where it goes. That number is lazy 8, which I've redefined. I didn't. The universe defines it for me. It's spherical infinity. So we're going to say that that's an imaginary infinity. And that is now a pseudo-number. I proved in 2022 that a spherical system will have a two-component number system, and that has been rigorously proved. That's the major breakthrough that I made in geometry, to prove that the linear number system, a one-component number system, is embedded mathematically in a higher order space called spherical space. And to compose that space, we follow Euclid. But not quite, because Euclid overlooked something, which is quite understandable even at this late date. But I discovered what Euclid missed. So did Einstein. So did Feynman. So did Dirac. So did everybody. They missed this relationship between two systems of conceptualizing the universe mathematically. Mathematically, that is, with numbers. You don't start with a line. But what I proved is you're virtually starting with a line, because there's a fixed constant relationship between any line and its sphere. And that's the embedding of linear space in spherical space. The spherical space, I proved, must have a two-component number system. It's based on proportionality rather than addition. So it's based strictly on the multiplicative identity. I think you know what number that is. It's not 0, that's the one for the line. This system has 1 at its center. It's the Archimedean balance of the proportional number system, is the number 1. It is sometimes called unity, which is not a numeric term. It's something a little more human. But that's how humans conceive of the number 1. It's a unit. That's the universe. Uni is not 0. It doesn't use that system. But that system is implied. That's why it works. And that's why Albert Einstein was able to linearize time. It doesn't mean that time is linear. What it means is that you have no way of knowing anything about time unless you linearize it. That's what Albert did, because space was already linearized. So Albert was obviously a genius, a seer, but he only saw through the grid. What we're going to do is compose the space in which Albert composed space-time. So we're actually conceiving space-time now. We're saying that time is in here. It's in the two-componency. It cannot be directly represented with one number because it's two numbers. It's space and time. That's what Albert proved. And in addition, he proved that linearized time is perpendicular to linearized space, which is a mind blower, because mathematically that means it's pseudo-hyperbolic space. We don't want that. That's not real. Space-time is incorrect. It's not real. It's localized to a specific frame of reference. What we want is space-time without a frame of reference. And that might seem like a contradiction. So having been thus forewarned, I'm now going to show you the trick that solves that paradox. What you do is you realize that you do have an Archimedean for spherical space. It's the number 1. But how do you get it? We know how to get 0. It's at the balance point of the straight line. But how do you get a 1 originally, just ab ovo? How do you get a 1? Essentially the same way you got the 0. Is by finding the Archimedean of the geometric space. The Archimedean of linear space is 0. The Archimedean of spherical space is 1. How can we prove that? By composing the universe according to its innate, natural, now to be made obvious geometric relationship between the center and the edge. On a line, the center is 0 and the edge is a bipolar infinity. That's embedded in spherical space, where the center is now not 0. We don't know what it is, but it's some other number that's the center. You have to have a center. That will be the frame of reference. And so all we're doing is changing the frame of reference of linear space to spherical space to get its center. And that's a two-component number. By the way, so is 0. That was proved by John Horton Conway, but we're not going to go there. That's a footnote, but leave a comment if you would like another lecture on that. I've given several in the past. But all of this must be repeated now. This is the first time I've attempted to go through the entire sequence. So you're in good shape, and I hope you're getting excited now. Because this next step is going to require your participation. This is the formulation of the spherical axiomatic basis that replaces Euclid. It actually does not replace Euclid. It's superposed on top of Euclid. This is the integral space that contains linear space. Much more powerful than Euclid could have ever imagined. The Greeks gave up on this. So did Dirac and Feynman and Einstein. Everybody's given up until today. So you have a two-component number system. This is axiomatic. We have to prove it. We're proving it now. We can get the number for the center and for the edge. Here's how to do it. This replaces plus minus linear infinity, which is a split infinity. This is split, but it's split in spherical space, not linear. So the center is one edge, and the outer edge is the anti-edge. Or you could say that the inner, whatever it is, it's not a point. It's not a Euclidean point, because that's 0. Even Euclid said that. Without using the word 0, that was not even discovered in Euclid's day, but he got the geometric 0. It's a 0D point. We don't want that. That's the center of the linear space. It's cubic or hypercubic. We don't want that. That doesn't match. We want the real one. The one that physics discovered in the 20th century. Everything is spherical. Well, now you need the correct number system. Here's how to get it. You need the correct object. It's not the line. Really, it's not the null point. Instead of the null point, which is 0, you want 1 at the center. That's the proportional Archimedean. Okay, so that's 1. How do we get it? By multiplication instead of addition. Plus 1 and minus 1 add to 0. Plus infinity and minus infinity add to 0. That can be proved. I did prove it. Well, it's already been proved, but I proved it in a special way. An integral form of that proof is very, very profound, and this is the outcome of that profundity, that insight. That you can make a number for the edge. And I think you will accept what I say, you have to make 2 numbers. 1 for each edge. And they have to be 2 infinities. Why? Here's why. Because the outer edge is infinity. It's spatial infinity. Can we give that a number? We're going to try. It's imaginary outer spatial infinity. That's lazy 8 over 1. Now we have a 2-component number. That's a relationship. It's proportionality. Spherical infinity over 1, we already know can be linearized to just spatial infinity. That is, spherical spatial infinity is the same as spherical spatial infinity over 1. Well, now we have the center. It's the reciprocal. So the center of the spherical system is 1 over infinity. That makes sense. It doesn't seem useful until you multiply them. What do they multiply to? What does 1 over infinity times infinity over 1 multiply to? It multiplies to 1. Where did the infinities go? That's the toughest question of all, but we're going to get it, but we don't need to get it yet. All we need to know is if it works mathematically. It does. So you have a center that's 1 over infinity. How do we define that? It's the reciprocal of the large number. Infinity is a large number. That's why we put it at the edge. How do we define that largeness? It's larger than any other number. With this characteristic, it's so large that it's imaginary. And that's its definition. That finitizes the universe, as you will see in a moment. So we have an edge that's a number that's imaginary, that's bigger than any other number. It's a super large number. Its reciprocal is proportionally small. And that forms the center of this system because it's smaller than any other number. Now how can we prove that? By multiplying them together. That makes one, and that's a harmonic sphere. It's just a sphere. Why do I say harmonic? It's balanced spherically between the center and the edge, so that the inside of the one is purely imaginary. And so the lowest number in this universe is 1, the surface of that smallest of all spheres. As you'll come to realize, that is the quantum, which is now relative. It's a relative quantum. It depends on what the two numbers are. Well, to get the original number, all we did was multiply two infinities together, and that gives us the center. That surface is the center. There's nothing inside. Because it's imaginary. Well, that means there's nothing there. That's a paradox, but we're going to accept it. Because we can do so logically, here's why. What's outside? What's outside infinity over 1? Nothing. There's nothing outside. It ends at infinity over 1. That's the largest number. That's it. That is the edge. Well, if you say that, you've also defined the center, which is infinitely small. So you can't reach either one because they're imaginary. But what's in between them is 1. So we have our first number in our geometric space. We have a 1, inside of which it's infinitely small, but outside of which it gets bigger and bigger until it gets to the biggest sphere. And there it ends. It ends at the outer edge and it ends at the inner edge. Everything in between is filled with whole numbers. Whole numbers. Max Planck proved that, but we're not going to go into detail here. That's the subject of my prior 670 lectures. But I am summarizing it now, but I can't explain every single thing. You're going to have to trust me at some point. But don't. If you're a scientist, you have to check. So I'll tell you how to check. In an axiomatic sequence, you make a hypothesis, which we just did, and then you attempt to prove it. Well, it's been rather daunting. Nobody's thought of doing this. Nobody's achieved the right sequence. This is the right sequence. When you say that infinity is imaginary and you turn it into a 2-component number, that number is 1. And the first number in the universe is infinity over 1 times 1 over infinity. That's one number. It's the number 1. That's magic. In the linear system, you get 0, which is a nightmare because it doesn't correspond to reality. There is no null at the center. There's a quantum. We just proved it. If you're clever, you'll see that that actually is a proof of what the quantum is. So we, in a sense, defined the quantum. It's 1 at the center, inside of which it's imaginary. Now you can see that it's there geometrically. Well, that's the paradox. What is inside that sphere if it's not space? I think you can guess. Let's prove it. We'll again use Max Planck. So now we have a universe that's not linear. I've proved that it is linear, but the linear system is embedded. So you can compose it from the spherical system. Technically and specifically, the linear number system is the derivative of the spheric number system. That's exactly right. It's the calculus derivative defined. What we just defined just now in this axiomatic sequence of postulates ending up with a proof, closing the circuit. We've established a number system for spherical space that's based on a complexification of imaginary space, which is kind of redundant. It's actually a complexification of infinite space. We have two infinities that are now balanced in a proportional system. That's spherical space, whose center is 1. Now, where are the numbers? This has to be rigorously defined. We'll do so now. It's not too challenging. I think you'll get this. It's easy for me to say because I can see it, but I recognize there may be a hurdle for you, so leave a comment if you have any questions. It's very important now to ask questions. This is the right time to ask questions. So where are the numbers? We have to have linear numbers. Accepting I proved that. So we do have linear numbers. Okay, where are they? Well, we have one number. We have the number 1. So just going in progression, where is 2? Is there a 2? Oh, there certainly is. Well, where is it? And can we measure it? Yes, we can. So we have the surface, which is a spherical surface with nothing inside yet. We're just saying that that's the surface of our space. You can do that. Riemann did it. So but you then have to prove that it makes sense. All right, so we have a 1. Well, how do you write that? It's 1 over 1 times 1 over 1. Those are two linearizable numbers. We hope. They better be linearizable or we got a problem. Well, I proved these are linearizable. 2 over 1 obviously is linearizable. It's 2. What about 1 over 2? Is that linearizable? Well, it is. But then you have to be cautious. Can you linearize all of the invert numbers, that is, the fractions? These are fractions less than 1. Yeah, fractions less than 1. So if you have a 2 as one component of your number, the other one has to be the reciprocal. That's the basis of the whole system, is the reciprocality of the center and the edge. Well, we now have one number that's harmonically in between. It's the number 1. All numbers inside that sphere are less than 1. All numbers outside the sphere are greater than 1, all the way to the edge. We call that space. So instead of space being linearized into a cubic grid, it's now concentric shells. That matches everything that physics discovered in the 20th century. So that's a big step if we can prove that this works. Because now we've captured physics in our mathematics system. Not capturable by linear systematization. It can't be done. Because the numbers are too awkward. And there's a 0 at the center. That destroys the system for universal space because space has no 0 in it. There's no 0 in the universe. That's an artificial number so that we can get linear distance. You have to have a 0 or you cannot have a distance. That's called the frame of reference. The frame of reference for the spherical system is a surface because there's nothing inside. So that's the center. That needs to be explained. What is that sphere? What is it? It's 1 over 1 times 1 over 1, but we haven't said what these represent. Well, we can say what one of the numbers is. Besides 1, 1 is a very special number. It's unity. So what about 2? 2 what? All right, let's do it. We now have spherical space with a 1 at the center. And so far, that makes sense geometrically. Now mathematically, we know we're not going to be using add and subtract. That's linear, based on 0, so we can't use add. Instead, the system uses multiply. We call it the multiplicative space. Essentially, nonlinear. that's what nobody understood, is that multiplicative space is the same as divisional space because they're the inverse, just like plus and minus are invert on the line. Well, multiplication and division are invert in spheric space. So these are division numbers. 2 over 1 is a division operation. 1 over 2 is the reciprocal division operation. These two reciprocal numbers multiply to unity. The basis, the equivalent of 0 in linear space, is 1 in spherical space. A surface that is spherical with nothing inside. Not nothing, imaginarity inside. We'll figure out what imaginarity is in a moment. This is where you're going to find time. So we have a higher order space now, an integral space, which captures linearity as a subsystem. It's a subspace. It's a subspace system of spherical space. That's technically correct, and I have to do this technically now because this is formal. So what do we do next? We go from 1 to 2. You can find out what happens in jumping from 0 to 1 on John Horton Conway's surreal number binary tree. But then he has day 2 where the number 1 jumps to 2. What happens then? You get two numbers, 2 over 1 and 1 over 2. One is less than 1, the other one is greater than 1. You'll see in a moment that greater than and less than is not the right relationship. It's not greater than and less than. It's proportional in harmonic space. That's strongly significant, but don't worry, I'm only including all these details for when the masters look at this, because they're going to tear me to shreds if I get anything wrong. That's the nature of science, not the nature of the brutality of the guys reviewing my work. You have to tear it apart if you can, so that no false information will be passed on to the next generation. That's the rigor of science that, of course, has been violated so rapaciously that words can't describe it. I intend to fix that. This is how. When you know that the next number after 1 has to be 2, then you know what you need to do to compose your number system. The first number in spherical space is not 1. That's the basis of the system. It's where you start from. What's interesting is when you start from 1 and you go in 2 directions, as you would on the line, plus minus, that's the linear split in orientation. It goes plus and minus. Goes plus and minus. On the sphere, it goes out and in. And those are reciprocal, not additive, multiplicative reciprocal. So, we now have a representation of the sphere. It's 1 proportion 1 times 1 proportion 1. The first number going out will have a reciprocal going in. If you view that linearly, you get Zeno's paradox, and here's how. You start at the surface of the sphere, here it is, and this is 1, remember, so 2 jumps out here to another sphere. It forms another sphere. This is the construction of quantum spherical space. The metric you have to decide later. What's the distance, the linear distance between those two spheres? That can be computed. That's why I had to... This has to be done very rigorously and provably. It's been done. So, the quantum jump from 1 to 2, going out, is easy to visualize. What about going in? We just said that that's imaginary space. Yeah, so we can't go there. So the half does not go in, unless it's into imaginary space. Instead, it's not going in. When 2 jumps out, 1 jumps sideways. It's orthogonal. That's what Einstein actually proved, is that space going out linearly in shells has a perpendicular direction to that spherical direction. And that is the sphere. That is the perpendicular line to the radial line. This radial line represents the jump from 1 to 2, but if you go in, you're going the wrong way, you go sideways. That's on the sphere. So one of the numbers is in space, the other number is not. It's not in space. It's in another domain. It's not a dimension. It's another domain. And this is the true dimensionality of spherical space. And you shouldn't use the word dimension because it's already been used for linear dimensionality. That's on a hard right angle. This is a soft right angle. And we'll be showing that to you in the Boschkovich force curve in just a moment to prove that that is continuous. That is a continuity. There is no hard right angle because that's a quantization on zero. This is not a quantization on zero. This is the integral solution in a higher space, permitting another degree of freedom. That degree of freedom is on the surface of the sphere. Space goes out in shells. Those are spheric shells, each of which is the same number, but with the two component numbers changing. Right? But the number going out is just one of the components. It's the whole number components. It's 2, 4, 8, 16. Think of it that way for now geometrically. You have the surface, inside of which is imaginary space, but going out is real space. Physical space. Physical space is being defined here, not on cubes, but on reality, on the curvature. This is purely curved space. So now you got the true dimensionality of the universe in one dimension, space. What's the sphere? What is that? First of all, it's perpendicular to space. Is it time? No. That's where Einstein missed. Space is not perpendicular to time when space is parameterized correctly on a two-component number, which we just established. The space number goes out, so that solves half the problem. What's the other component? It's energy. The surface of the sphere represents energy. Energy is not space. Energy is not even spatial. Energy exists in the other domain. Why? Because it's motion. You could say that one is the aspect of the other. You could also say that they're equivalent. That wouldn't be quite true because we have a linear conception of momentum. That's what Newton used. We can't use that anymore. That's linear force. There's no such thing as linear force. The universe only has two dimensions, space and energy. Now, on the sphere, that's where energy is. So it's a spherical phenomenon. And space is related to that in the sense that going out, it has to conform to the shape of energy. And it does. Space is spherical. From anywhere you look in the universe, space is spherical. That is absolutely correct to a threshold. We'll be talking about hypersphericity in a moment, but it's not strictly speaking necessary. But it's still there. Now what we're getting to is the actual geometry of space-time. But now you can see that it's not space-time, it's space energy. And I've already told you why Albert was able to orthogonalize those. It's because space was already linearized. We're not linearizing space, so there is no linear orthogonality any longer. If there is an orthogonality, we'll have to rediscover it. We just did. The radial line going out from the center can be thought of as the radius of the sphere, but it's not a linear line, it's this line going out. So it's a force line. That represents force. Now in gravity, it's force going in. In light propagation, it's force going out. And those are the two balancing forces, as we'll find out, that describe the entire universe. But we need to be rigorous. It's easy to make prognostications, but all of this has to be rigorously proved. So let's continue with our rigorous approach. We now have concentric spheres of space that form the number system for space. The perpendicular space is the surface of any of those spheres, but they have to be conformable to the surface at the center, which is a sphere. So all the spheres have the equivalent surface. You can see they get bigger, but they're still the same sphere. So force is responsible for the dimensionality of space, which is simply going out. Space goes out. From anywhere you are, space goes out. It's so tautological, it seems like you shouldn't even have to say that. But that's a strict statement of truth. Space always goes out. Space goes out from a center. Okay, that brings in the notion of the center of consciousness or the center of measurement. It forms a measurement problem of the quantum paradox complex, which we're going to crack right now. The universe is the frame of reference. We have the reference frame itself. This supersedes Einstein. To do what he was trying to do, even to the end of his life, he was trying to get a non-inertial frame of reference. Well, the light cone simply fails, so we need to start over. That's what we just did, and now we're at the solution threshold. So now we have spherical space, but we need to get motion in there somewhere because space has none. Well, that's on the surface of the sphere. That's the perpendicular dimension in spherical space. What is that? It's a rotating sphere. So it has an equator of motion called its angular momentum. That's actually a characteristic of state. So now we're talking about the state of the system. That always implies motion. When you're talking about state, you're talking about motion, and you're attempting to quantize it. You can't do that with linear numbers. It'll quantize to two numbers that don't relate at the inner limit. That's the quantum paradox. We need to solve that. It's directly solved by transitioning to integral mathematics. That's what proportional space allows. Integral mathematics. So how do we do that? We look at the sphere now, whose characteristic is angular momentum. Angular momentum is the only known source of motion. All motion is reducible to angular momentum. So all motion is on the sphere. Space has none of that. But you can see that in the two-component parameterization of spherical space, only one of the components represents space. The other number represents a relationship. And space will relate to that. So space we have, it's the whole numbers going out. Now we need the fractions of 1, beginning at 1/2, the highest possible wavelength, because it's the reciprocal of the frequency, and frequency times wavelength equals light speed. So we're talking about, when we say 1, the surface, we're talking about light speed. So the characteristic of the sphere is that it captures or encapsulates light speed. Well, that's a two-component number. In spherical space, you have two subspaces. One of the subspaces is spherical space in shells. Those are quantum shells of space. That's correct. The quantum jump is actually a spherical jump. So that's a much better conceptualization of space because it matches reality at all levels. There's a footnote. The universe is very interesting, but this is the right way to conceptualize it in the human mind so we can use our mathematics in conjunction with the geometry, which I discovered. Switching now to the surface of the sphere, we're in a subspace. and it's not space. It's exactly what space is not. It's perpendicular to space. So the surface of this sphere, the one that has the value 1 over 1 times 1 over 1, we know that the 1 over 1 in one component will be space. And the other component is on the sphere. And it's also 1 over 1. We'll return in a moment to why space is 1 over 1. But what we're looking at now is why is the sphere 1 over 1 on its surface? It has to be relating to quantities. What are they? Well, one of them is going to be 1, but the denominator changes. The denominator changes to the proportion that the spatial numerator changes. So is this number going out to make spaces 2, 4, 8, 16 all the way to the edge of infinity? The conjugate number is going perpendicular as motion in another domain, and that's energy. So energy is a two-component number. Yes, it is. It's frequency times wavelength. And that is computable on the sphere. So that frequency times wavelength, for any form of electromagnetism, frequency times wavelength equals light speed. So in that sense, light speed can be considered constant because it's always represented as the number 1 in normalized spherical space. That light speed, by definition, is 1. And that 1 is that sphere. So now we're looking at the sphere, the surface. So that surface is represented by another parameterization of two numbers, leaving open the question of how is space going to be a two-component number. We're linearizing it when we say it's 2, 4, 8, but it's actually still a two-component number. You still have to explain the relationship. We're getting there. But in order to get that, we have to understand the reciprocal space. It's perpendicular. Reciprocal and perpendicular, turns out, I discovered this, are synonymous. It's a spherical right angle. So that's going to be the perpendicularity that Albert discovered in linear formulation. The derivative number system reveals that relationship, but it's indirect. In spherical space, it's the perpendicularity of space and energy. So where is time on the sphere? It's one of those two component numbers, which in this case, for the lowest frequency, which is 2, representing the first real number, spatial number is 2. The lowest spatial number is 2. Well, that's the frequency, you could say, but here it's not. I mean, here it is. There we have to define what that 2 is. We know it's outside the 1. That's why it's 2. We'll get back to that. I've never actually broadcast that specific relationship, but it's immaterial at this point because we're done with space. Spaces make sense. The numbers fill space. The whole numbers fill space with concentric spheres. That perfectly parameterizes space with that strange gap between the spheres. That's the quantum jump, which we need to define because that must be continuous. But it also must be quantizable. That's a direct contradiction called the quantum paradox, which exists in linear space, but it also exists in spherical space. We still have to explain the jump from 1 to 2 and 2 to 4. Why is there a gap? What's in there? There has to be something in there. Otherwise, this is just a mathematical construction of space. It could mean nothing. It's the opposite of nothing. It means everything. So here's how. The sphere can be parameterized, just the surface, without respect to space. It's parameterizable on angular momentum. Every sphere in the universe has an angular momentum component. So, how do we analyze that? What does that mean? It means that the continuous line of the sphere, which would be the equator of rotation, that's called the eigen of the sphere, is its angular momentum component. You could say that that creates the sphere. So angular momentum has this interesting quality that we can compute it on a circle, but then we need to translate it to a sphere. That's very interesting. We're just going to approach this logically on the obvious, which is the equator has the eigen of angular momentum. How do we measure that? We measure it in cycles. Fractal Woman has some excellent presentations on this. This really baffles the physicists themselves, so we're really dealing with some innately tricky territory here. Angular momentum is very interesting in its conceptualization because you're not talking about space. Remember, this is not spatial. What is it then? It's temporal. It's temporal. Temporal space is perpendicular to what we call physical space. So it is perpendicular, and now we know why. It's because it's on the sphere as the eigen of angular momentum. That is measured in cycles. So now the number 1 represents one cycle. It's a closed line. It's not a linear line. It's a closed line, so it doesn't have 2 open points. It has an infinity. That's called continuity, and therefore one revolution, that is one cycle, is not in space. It's in time. That's how Albert said it. So what does that mean? You see, we're homing in on time. It's on that sphere. It's not spatial. So far, so good. We already know all this. So what's the key insight that gives us the geometry of time? It's to understand the relationship on this, the eigen of the sphere. Why is there motion? What is motion? It's this cycle. Click, click, click. You hear it. Click, click, click. That's time. Well, do we know that already as a number? Yes, we do. It's called frequency. That's frequency. That's not spatial. Frequency is non-spatial. What about wavelength? It's a length, so you would be tempted to say that that's spatial, but you would want to hesitate there because we already know what's spatial. This is not spatial at all. So wavelength is misnamed. It's misleading to call it a length. It's not a length. It's an aspect of temporality. So time is a little bit more complex than Albert ever suspected, or if he did, he was unable to solve it, and he tried. Right to the end of his life, he tried for the grand unification theory, sometimes called the theory of everything. It doesn't matter what these grandiose terms intend to imply. You simply want to get the right term. Unification of physics. It's the unification of physics. All right, so we're getting there. We've got space. It's going out. But on the surface, we have something that has an eigen of angular momentum that's a 2-component number, neither of which component is spatial. But one of them is time. It's the frequency. The frequency in relation to what? It's the frequency in relation to what the frequency is dividing. And that's the quantization of time on the circle. It's the cycle. But it's more than just the cycle, because the cycle is merely the frequency. Click, click, click. What is going click, 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 click? It's still a frequency. It's a higher frequency, isn't it? That has an effect on the wavelength. Let's look at it so you get this firmly in mind, because this is the breakthrough insight. If you see this, you're going to see where time is. On the click, 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 there are 2 aspects. One is the frequency. Click, 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 or click, 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 click. What does that do to the distance, the wavelength? It decreases it. If the frequency is 2, then the wavelength is 1/2. Max Planck, so there you go. That's the lowest frequency in the universe is 2. That means that the highest wavelength is 1/2 in relation to that 2. Can we see that geometrically? Take a look at the circle with me. Just draw a circle in space. Put 2 dots on it that are antipodal. That means you're drawing the diameter and those 2 points. Consider that to be the frequency. Can you see the wavelength? I think you can, because the cycle has been divided in half, because now the frequency is doubled. When you double the frequency, two points, well, that's the lowest frequency, is 2. Well, you can see why. That's the fewest number of points that you can put on the circle to make a relationship. If you have just 1 point, you have no frequency and no wavelength. Yes, you do. You have a frequency of 1 and a wavelength of 1. That's the frequency of the universe and the wavelength of the universe. Both are 1. That only occurs, as far as we've been able to find, in light speed. Light speed is always 1. That's why. It's because it's frequency times wavelength. What can we say then? Well, what if you put 3 dots on the circle in an equilateral triangle? Let's keep it harmonic and not deal with odd numbers. There's a reason for that, but don't worry, because this all works. But let's make it simple on ourselves and use even numbers, because we are dealing with 2-ness, right? 2 is the lowest frequency. What if it goes up to frequency 4? Well, that's double the frequency. What happens to the wavelength? It's halved. How can you visualize that? You have 2 dots, frequency 2. Now make 2 more. And now you've divided the circle into 4 parts. That's 1/4. That's the wavelength. So it's always 1. It begins at 2 because if you have 1, you have 1/1 times 1/1. That's what we just proved. But if you break that, that's called symmetry breaking, by the way, and that's the only symmetry break in the whole universe, is the symmetry of the circle on the frequency wavelength relationship. But you can see nothing breaks. Nothing breaks. It's smooth. But it is quantized on 2. That's the quantum jump, is from 1 to 2. Because that creates the lowest frequency, because that's a vibration. That's called a harmonic, and that's the simple harmonic oscillator. 1 to 2 to 2 to 1. 1 to 2 to 2 to 1. A very special relationship. It defines the universe in terms of energy. That's the energy equation. Frequency times wavelength is light speed. So now we know where time is. It's the frequency. So time is related to another number called wavelength. And you can see where that is. It's the division of 1. It's the division of 1 into parts. The reciprocal of that is the division of space into parts, in concentric spheres going out, based on the eigen of momentum, which is energy, or you can also call it motion. It's a 2-component number in any case. Well, frequency is one of the 2 components, actually. Frequency and wavelength are always 1 number, and it's always 1. Isn't that interesting? We'll go on with that, but that's an hour and 45 minutes. That's a little over 100 minutes. That's enough for anybody. I hope you took a break. Thank you for tuning in. This is just the beginning, but I hope I helped you to see where space and time meet. Once you have spherical geometry, it all makes sense. Frequency now is a meaningful term. It's time. And so time is always related to another number, which creates unity. But time by itself is merely an aspect of a two-aspect thing, because this is continuous and can only be thought of as two things, neither of which is spatial. Isn't that interesting? I hope you enjoyed this. I certainly did. I learned something from each one of my lectures. But science is communicative, so I hope that this can be ultimately proved such that others can accept it. Otherwise, either I'm wrong or it doesn't matter if I'm wrong or not. That's science. And that's why it's a challenge to try to express this sort of information. I hope it helped you. I sincerely hope, because that is the purpose. Science is to help people orient so that you can get what you need according to your blueprinting to live out your life correctly, so that you can mean something. You already do. You simply want to complete what's being begun for you the very best way possible. I'm trying to help. I'm not trying to bring down any pillars. I'm trying to add the science. We'll be right back. Keep looking up. We'll have another presentation later today, I hope. I say I hope. It's cooled down enormously here in Chico, so we're out of the 110-degree days, but they will begin again in 5 days. So we have another phase of 110-degree days, but for now, this is a golden window to shine as much as I can. We'll be right back. This is Galactic, bringing you the secrets of the universe.